Welcome to a video on power and energy and generated from solar panels. This is kind of an introductory lesson. It has a few basic examples. We're going to talk first about the difference between power and energy. So energy is the capacity to do work. And so it might be something that provides light or heat or movement. And that's as simple as just movement of atoms even. That's energy. The capacity for something to move. Now power is the rate at which energy flows. And energy flows, it can be radiated, it can be absorbed, like heat is absorbed or dissipated. Like a rock rolling down a hill. Energy is flowing. So an example of that is if you're carrying 50 pounds up a set of stairs, that requires the same amount of energy whether it takes 10 seconds or 20 seconds. But it takes more power to carry the weight up faster. So in fact it would take twice as much power to carry it up twice as fast. So the same amount of energy to lift something, but if you lift it faster, it's greater power during the time that you're actually doing the lifting. So let's talk about the units for power. Watts is a unit of power, and that is how fast energy is flowing. You can think of it as water, in fact, like water through a hose. The faster the water goes through the hose, would be the faster the energy flows, is like a greater power. So, it makes sense. More water pushing through a hose at the same amount of time is going to be more powerful. And in energy, we measure that in what are called joules per second. So you can think of energy as these little packets, little joules are like little energy packets. And how fast those energy packets are moving, that is what power is, a joules per second. So think of this as in water, you might measure it in gallons per minute, for example, how fast something fills up. So gallons is an amount of water, and you could think of joules as an amount of energy in that respect. So an example is if you operate a 50-watt incandescent bulb. Now remember, watts is a unit of power. So that's how fast something's energy is moving. So or being transmitted or absorbed or radiated. In the case of light, it is energy that's being radiated. So operating a 50-watt incandescent bulb for 2 hours requires the same energy as operating a 100-watt incandescent bulb for 1 hour. The higher wattage, that is the 100-watt bulb, requires more power. Watts is a measure of power, so this is twice as much power as this. So if you run this 100 watts for an hour, that's 100 watt hours, if you will, and 50 watts for 2 hours would be 50 times 2, so it also gives you 100 watt hours. So that's the amount of energy. You take the watts or the kilowatts times the time, and that gives you your amount of energy. So 50 watts times the 2 hours gives you would be 100, and we'd call those watt hours. And of course 100 watts for 1 hour is just also 100 watt hours. So keep in mind, it's the rate that electricity is transmitted is power. And so the rate electricity is transmitted into a home is measured in kilowatts typically. Now remember, kilo means 1,000. So this is like 1,000 watts. And that's how fast it would come into your home if you're using it. And then you pay for kilowatt hours, and that's a measure of total energy. So our power bills come in how many kilowatt hours you have used. That's how much energy you've used. Some people call it a power bill, but it's really an energy bill. So now as we move on to solar power, power from the sun, because that's light is coming from the sun, and light is energy. 1 kilo is 1 kilowatt per square meter. So sunlight, direct sunlight that is, provides just 1 kilowatt per square meter. That's 1,000 watts. So solar panels today are only about 20% efficient. So when the sun is shining directly on a 1 square meter solar panel, the power transmitted from the panel is only 20% of that 1 kilowatt. So you only get 0.2 kilowatts if you had think of a wire coming out from that panel, which we do have. Panels have wires coming out from them, and that wire would only be generating 2 kilowatts. That's how fast the energy would be flowing out of them. And that's 2 kilowatts is really 200 watts, right? Because 1 kilowatt is 1,000 watts. Kilo meaning 1,000. So let's just do the simple problem of how much energy can be transmitted from 50 square meters of solar panels if they are exposed to sunlight for 4 hours. So really, you think about it as we have 50 square meters of solar panels, and we're really doing a conversion. We're going to take 50 square meters, and I'm going to write square meters in that fashion. That's 50 square meters of solar panels. And what's happening is we get 1 kilowatt per square meter is how much energy the sun's providing there, or the power of the sun there. So it's 1 kilowatt, and notice it's per square meter. So that's going to be 1 kilowatt over 1 square meter. Well, that should be just 50 kilowatts, right? That's the amount of power potential. However, the solar panel doesn't actually take all of that energy and directly convert that light energy to electrical energy. It only is 20% efficient. So while this would give us 50 kilowatts, but the panel, once it is leaving the panel, it only can generate 20% of that. So 20% times 50, of course that 20% is 0.2, so that's equal to 10. So that will give us 10 kilowatts, and that is the power, that's the rate that electricity is leaving the panel. But it says it's going to run for 4 hours. So we take that power, the kilowatts, 10 kilowatts, and you multiply it by 4 hours. And that will give us 40 kilowatt hours. Okay? So that's the basics of how this is an amount of energy. This is an amount of power. Kilowatts is the power. So let's take, for example, a microwave oven. Microwave ovens require 1,000 watts. That's normal for a microwave oven, which is 1 kilowatt. So a microwave oven needs 1,000 watts to operate. On Mars, the power from the sun is only about 500 watts or 600 watts per square meter. Now remember, back on Earth, it was a whole kilowatt per square meter, which is 1,000 watts. So this is quite a bit less on Mars. The power in kilowatts transmitted from 150 square meters of solar panels on Mars, what's the power if they are 25% efficient? So let's calculate that power in kilowatts. So in this case we have 150 square meters, and instead of 1 kilowatt per square meter, we only get 500 watts, which is 0.5 kilowatts or 0.6 kilowatts. And it doesn't tell us which one to use. So let's use the 500 watts. That's probably a little more accurate, actually. I think it's closer to 500 watts on Mars. So 150 square meters times 0.5 kilowatts. That would normally give us, well, that's half of 150 would be 75 kilowatts. But The solar panels are only 25% efficient. So we'll multiply that by 0.25 or times 1/4 if you'd like. That's the efficiency rating that you have to multiply by. So 75 times 0.25, I think that's 18.75 if you do that on your calculator. So that's what would be coming out of a 150 watt solar array, is 18.75 kilowatts on Mars. Now, how much energy in kilowatt hours is transmitted from those solar panels in 6 hours of exposure? So we just take the 18.75 kilowatts, multiply it by 6 hours, and there you go, whatever that is, 18.75 times 6. Did that on my calculator. And that's 112.5 kilowatt hours.